Welcome. My talk is called Out of Memory or Plenty to Spare, the Fine Details of Reading Memory Consumption. First, a few disclaimers. First of all, I will not be talking about PHP. So if you think this talk is about how memory works with PHP, then I'm sorry, this is not the talk for you. But what I will talk about is how memory usage works in general. So not only for PHP, but pretty much for every application and operating system. It's going to be some pretty advanced stuff, but I will try to simplify things. So if you think that I'm saying something wrong, it's probably because I simplified things because it's way more complex than I can actually tell you in just 50 minutes. So, a question that pops up a lot is this: how much memory is our server using, or our laptop, or our computer? And this used to be a fairly simple question, but in the days of the operating systems that we work with now, this is not an easy question to answer. In fact, this is a question that we pretty much cannot answer exactly. And this talk is about showing you why is that? Why am I not able to ask a computer how much memory do you have left? Who of you know this interface, this command, this program? Wow, that's a lot. Even with the nice red colors? Cool. Have you seen the purple ones and the green ones? That's also there. Oh, okay. There's even more. Okay, so when people come to me and say, okay, how much memory do we have left on our system? I'll just pop up a command called top, or htop if you like that. And I'm just staring at the numbers and I'm like, yeah, I have no idea what I'm doing. It gives me all kinds of data, but I can't make anything out of it. Besides top, there's actually another one, command line, and this is just for Linux, and that's called free. And free gives us all kinds of information: total memory usage, used memory usage, free memory usage, available memory usage. So it's still really hard, so which one is the actual number that we actually need? Because you would think it's free, but actually it's not. It's available, and even that is not completely true. And the reason for that is that Linux or Windows or OS X or pretty much every modern operating system are really smart dealing with memory. And it basically does all kinds of changes in memory depending on the workload and what you want. And one of the things that it does is if it sees that you have free memory left because you only run 1 or 2 applications, then it will say, there's so much memory, I will use it for caching, for instance. And this is what memory normally looks like. You have stuff free, you have a block that is actually used in memory, and you have a large portion that is called buffers and cache. This is basically the operating system using as cache. So the available memory is not just the small green free block, it actually is the free block plus the buffers and cache. Because as soon as you start to use memory, the buffers and cache block will also degrade. It will use less cache and more memory will be available for your applications. So it will be, it's a dynamic number to be exact. So buffers and cache is a dynamic thing and it depends a bit on how much application memory that you are using. So what's inside buffers and cache? And this is something that you can answer with a tool called Slaptop. I don't know if you ever heard about it. Slaptop is a really cool application. You can see all kinds of information, what's inside. And the top part says ext4 inode cache. And basically this is the file system caches from Linux. So this is a very large number. It's how much? 825 megabytes, I think. Yeah. So that's a large number that is just cached for files. Actually not files, but the file inodes. And this is not a problem because as soon as your application needs memory, this will drop down. So this is what's exactly in the cache. There are things like dentry, which are directory entries, buffer heads, all kinds of stuff in there that will be dynamically scaled up and down. So how much memory is our application using? Now, this is again a very, very hard question. And before I can answer that, we have to go a little bit in depth into how a computer, or at least an operating system, works. And one of the basic foundations are processes. And I think we all understand what a process is. A process is pretty much any application that runs on your system. And a process is completely isolated from another process. So for instance, if you have PHP FPM running, and you have Nginx running, and you have MySQL running, those three processes, those three applications are not aware from each other. They can talk to each other with telnet, with TCP IP ports, for instance, but they are completely separate from each other. The operating system will separate them. This means that they can act like they own the place. And that's true. They can say, okay, listen, I'm just here and I'm the only one here, so I can do pretty much whatever you want. This is not completely true, because if it does something that's not allowed by the operating system will kill that process, and you will have to restart it again, for instance. You must ask permission for pretty much everything you want to do. So applications are allowed to do their business logic, but as soon as an application wants to read something from the network, or read something from disk, or even write something to the screen with a simple print or echo statement, it must ask the operating system to actually do that. And the operating system will check to see if you have the current permissions. Can you read that file? Are you allowed to read that file? Does that file even exist? And then it will say, okay, here's the file, or it will say, no, sorry, you can't read the file. So everything must be done through the operating system. And it looks something like this. So we have 4 processes: Nginx, PHP, FPM, MySQL, Redis, and they're all separate from each other. So everything that Nginx does not interfere with anything that PHP, FPM does not interfere anything with MySQL, etc. And everything is communicated through the kernel to the operating system. This is true for Linux, this is true for Windows, this is true for OS X, and pretty much every operating system. Now, if you are a process, for instance, Nginx, and you want to say, oh, listen, I'm here on my own on the system, I want to get some memory because I want to put a web page in there, or whatever you want to do. That memory has to come from somewhere. So let's say you assume you have a memory block and you're going to use that, and PHP FPM at the same time says, oh, I want some memory as well, and I want to use the same memory block as well. And they don't know each other because they're separated. But that isn't really that problematic, because there is a difference between memory in the processes. There's a difference between memory. You have physical memory, which are the chips, the DRAM chips, or the SODRAM chips, and you have virtual memory. And virtual memory is basically the one what you're dealing with for every process. So if a process is going to allocate memory, it's going to allocate virtual memory. It has nothing to do with the actual physical memory chips on your system. That's going to be dealt with a little bit later on. So what's virtual memory? Pretty much every process can access up to 4 gigabytes of memory. We're talking about 32-bit machines. If you have 64-bit machines, it's a bit different, but to simplify things, I'm using 32-bit machines. What a process can do is say, okay, I want 4 gigabytes of memory, and the operating system can give you 4 gigabytes of memory. Even if your computer does not have 4 gigabytes of memory. Nowadays, 4 gig is pretty common, of course, but this also was true by the time that you only had like 16 megabytes in your system. You could still use 4 gigabytes of memory, virtual memory, while you only had 16 megabytes of physical memory. The other way around is true as well. If you have more than 4 gigabytes of physical memory, your application or your process can only use 4 gig. It cannot use 5 gig. So the 4 gig is actually a virtual memory limit. On 64-bit machines, it's a bit different. You can actually, in theory, you can use 16 exabytes, which is a large number considering in 2013 the size of the internet was 672 exabytes. So I don't want to know how much it is now, but it's a large number. But often, due to hardware constrictions and even software constrictions, the virtual memory is normally between 8 and 128 terabytes. And that's, for most processors, more than enough. I don't know what you want to do with an application that uses more than 128 terabytes. That's a very large database, I guess. I don't know. On 64-bit machines, the number is a little bit larger, but the same holds true. So on a 32-bit machine, your memory, your virtual memory, looks something like this. It actually is split into two regions. There's a 1 gigabyte region on top, and there's a 3 gigabyte region downstairs. And that downstairs region is what the application can use, your process can use. And the 1 gigabyte on top is actually reserved for the kernel. So an application cannot touch that memory. If it's gonna go into that memory, like read a byte from that memory location, somewhere in the red in the red square, then your operating system will actually shut down your process with a seg fault. If you ever see one, it's probably because you read invalid memory. There's a little bit of memory at the bottom as well that you're not allowed to read as well, but it's a very small part. So most of the 3 gigabytes is available for your process. On Windows machines, 32-bit machines, that was actually a split between 2 gigabytes and 2 gigabytes. So you had 2 gigabytes for the kernel and 2 gigabytes for the application. But you could also change that. So normally 3:1 is the most common split. So you're not allowed to touch that as an application. Only the kernel, the operating system, is allowed to touch that memory. So what happens? Your application gets placed into memory, into virtual memory. And it's put, for instance, at this place. So this blue block is basically your program and your data from that program. Besides that, it will also add some, for instance, shared objects, DLLs or SO files. They are placed somewhere at the top. And there's normally a stack. And the stack is where we place temporary things, function calls, etc. And that stack is up there. And if you know thing about stack grows downwards. So it starts at the top of the stack and then it grows downwards to the shared memory block. And as soon as you hit the limit of the stack, then you get a stack overflow. So the stack overflow is actually literally the stack overflowing or underflowing if you go downstairs. So pretty much the green part is free for applications, but applications are not allowed to touch it directly. If an application says, okay, so I'm loaded into memory, I want to allocate some memory in that green spot, then I want to read some memory in that green spot, it will actually segfault as well. You're not allowed to touch that at that moment as well. And the reason for this is that that memory is not allocated yet. It's available for the system, but it's not initialized to say. So to give you an idea how this works, that small block of that memory is partitioned into smaller blocks, into 4 kilobyte blocks. And every block has its own memory location. So there are four kilobyte blocks where there is some data and applications, and there are 3 blocks that are not allocated as well. So if I want to read something from address 12343 something, then I will read something in the top blue block. If I read something from 12345, then I get a segfault because that's inside the green part, and the green part is not allowed. You cannot touch that at that moment yet. So this is virtual memory, but in the end it needs to be inside physical memory. Virtual memory must be placed somewhere. And this is where the neat thing of memory management comes. And that's because all those addresses doesn't correspond with the actual location on the physical memory, but can be anywhere. And what happens is that there is something called a page table, or actually which is a phone book, where every virtual memory location will be listed. And besides that virtual memory location will be a physical location as well. So what happens is that in that phone book, it says, for instance, virtual memory 1234000 actually is located in physical memory at address 1000. If you go to memory location 12341 3 times 0, then you have to go to physical memory 5222000. So what it does, it actually takes every virtual memory block and connects that to a physical memory block. And this is what is called the page table. And every process has its own page table. Only the pages that your application uses, so only the blue blocks basically, are filled in the phone book. So a phone book starts with a very small phone book with nothing, of at least not a lot, filled in. And as soon as you're going to use memory, more pages will be filled in and more will be mapped to physical memory. If you want to map all the 4 gigabytes of virtual memory, then that page table would be around 4 megabytes in size. So it's fairly small compared to the actual memory that is going to be mapped. Because virtual memory is mapped to physical memory, that means that every virtual address that is used in your application must be converted to a physical address through the page tables. And this is what a CPU does through something called a translation look-aside buffer, the TLB. It's basically it's not a very big cache, but it's a cache where it says, okay, I want to go to this virtual memory location. That's physical block, this, and you can look it up. This is why it's fast enough to actually go from virtual memory to physical memory. So how does it look? Suppose I have a process and it has 3 memory blocks, 1A, 1B, 1C. And that's somewhere stored in physical memory. Let's say it's stored here, so it doesn't even have to be stored sequentially. It can be literally all over the place. We have no idea where blocks are stored. If we have a second process, also with block 1, A, B, and C, it can store it also in physical memory. And again, it's not sorted or sequential at all. Same is true for the third one. We can place it inside the same physical memory. But now we have a problem. Because now we have a fourth application, and that fourth application needs 3 blocks. But we only have 1 more block free in physical memory. So in this case, what the system does is going to take a look at, okay, so I don't have enough memory, not enough physical memory. I'm going to take a look at what the blocks are that are not used a lot. So for instance, block 1C and block 2A, they are not accessed since a long time. And it will actually put it inside a swap space or a swap file or a swap disk. So it moves those blocks out of physical memory. It will mark in the virtual page table, it will mark that those blocks are not on physical memory but are actually stored in the swap space. And now we have room to actually get our fourth application in. And this is what swap space of swapping actually does. As soon as you're going to swap something, it means that there is not enough physical memory to actually hold all the blocks from all applications. So it's going to take a few blocks, as many as needed, put it into a swap space or swap disk, and make room for other applications as well. When this happens, so for instance, let's say that we have our application 4 in. And now application 2 needs to access block 2A. That's possible because the application doesn't know anything about swapping, but 2A is not a physical memory. So what happens now is that the CPU tells the operating system, listen, you want to access a block of physical memory, which is swapped out, and the operating system will actually take a look, where did I put that block, place it in memory. The operating system returns control back to the CPU, and the CPU can continue how it was before. And the process, process 2, is never aware of this. So an application does not know if it's going to access a block of memory that has been swapped out. It takes a little bit longer before the access actually completes because it needs to read it from disk. But the process by itself doesn't know anything about swapping. That's something between the CPU and the operating system. So in quick recap, every process can use up to 4 gigabytes of memory. Every process gets its own page table, its own telephone book. Every process starts with the smallest possible page table, so it doesn't use a lot of room. And pages can be swapped in and out of memory by the CPU and operating system, unaware by the process. So, what happens when a process wants more memory? What happens then? So, let's go back to our application. And we already know that we cannot access that green part. So we have to ask the operating system to actually give us more memory. So you're going to ask the OS through 2 function calls. These are not in PHP, of course, but they are in lower level languages like C. It's called break or sbreak and mmap. What sbreak does, it changes the data segment size. And it looks something like this. So we have our application, and we're going to say, okay, I want to reserve 10,000 bytes of memory. At that point, it's going to take a look at where the top of your application is, and it's going to add 10,000 bytes to that. So the heap, what it is called, will increase with 10,000. So now there is a light blue block where an application can actually access the memory. And what happens here is that sbreak does not really allocate physical memory, but it actually creates table entries in the page table. So what it does, it actually creates memory by filling in the phone book. It doesn't fill in what physical address is it stored, but it's going to fill in, listen, I'm going to use this virtual memory addresses. So allocating is actually pretty fast. The thing is, when you allocate memory, the physical memory usage stays the same because we don't allocate physical memory, but we do allocate virtual memory. And I can demonstrate that with a very small application. This is C, but I guess most of you can read this. So what this does is I'm going to allocate 1 gigabyte of memory. That's the only thing that this application does. And when you run it, you can actually see in top the results. And you see in top the command is called memory, that's our application. And you see in the column vert, you see 1027 megabytes. So what it did is it reserved virtual memory of a little bit more than 1024 megabytes, because there was already probably virtual memory there. So that's it. And the res column is actually our program and data. That's actually the very small application that is running that's only 400 bytes in size. So that doesn't grow. So this virtual memory is grown. But basically the virtual memory only says how big is our page table. It doesn't say anything, did we actually use that memory? Because still no physical memory is being allocated. Only when you access that virtual memory, so when you physically read, or actually your application reads that virtual memory, then the actual memory usage will go up. And only pages that are accessed will be created or loaded into physical memory. So allocating 1 gigabyte of memory is a very cheap and very fast process. Iterating over 1 gigabyte of memory is not, because it needs to literally create or allocate in physical memory that 1 gigabyte. And this is another example. It's a little bit different because I'm using malloc for that, but that's just a wrapper around SBreak for the time being. So I allocate 1 gigabyte of memory, which is very fast because it only increases the page table and the virtual memory column will grow with 1 gigabyte of memory. But then I will iterate over every memory block and I place a 1 inside. So it needs to allocate for every block in that 1 gigabyte memory that I just allocated. It needs to allocate physical memory as well. And if we take a look at top now, you can actually see the virtual column is still 1027 megabytes, so that hasn't changed. But the residential, is now 1.0 gigabytes. So now that has grown because we actually used that memory. We didn't only allocate it, but we actually use it as well. There's another command besides SBreak, which is called mmap. This is used a little bit more nowadays. It's also lazy loading. What it can do is it can map a file from disk into memory without explicitly reading it into memory. It creates virtual memory that is not mapped to physical memory, but is actually mapped to things on disk. What it does, it can allocate, you can also use it to allocate memory, but what it does, it creates random blocks of memory mapped data, so it's all over the place. It doesn't have to be a continuous block of memory, which is happening on SBreak as well. There's a tool called PMap, and if you take a PMap and you add a process ID to it, you can actually see the virtual memory addresses there and see how it's mapped to certain stuff. So you can see that the top one, the 1EE000, is actually mapped to a libgs AP KRB SO. You also see that there's a PHP FPM running on 804800, which is the start point of the PHP FPM application, so it's always on that same location. And you see all kinds of memory blocks that are being created that are either mapped to files or to gconf modules.cache, but also to to a file called 0. And basically what it does, it maps a certain block, in this case a 128 megabyte block or 131,000 bytes, and it maps it to def0 or def0, which actually creates a zeroed out block of memory of 128 megabytes of memory. So you can actually take a look inside a process to actually see what's happening and what's actually allocated in virtual memory. So again, this has nothing to do with physical memory because we only can see what's mapped in virtual. So we now know that the virtual column is not really the thing that we need to take a look at because that's not really very important. The residential says a little bit more because that's code that actually is allocated in physical memory but could also be swapped out, so we don't know exactly if it's the same thing. But there's another problem as well, and that's this. So suppose I have 3 processes here, and they all have allocated data, and they all have stacks, and they all have shared objects, and they all have application data and code. And what happens is that some processes can actually use the same physical blocks as other processes. So suppose I have 2 processes, again 1 and 2, and they're all the same code block of the same applications. What can happen is that they are allocated in physical memory as A, B, and C, and they all point to the same blocks. So 1C is the same code block as 2C. So in this case, you can actually have memory that is linked together, but they are in separate virtual spaces. And this is something that an application of that happens when you actually fork applications. And fork is something that you can use in PHP as well. Anyone ever used fork? Yeah, cool. What fork does is pretty much, it's actually very easy what fork does. So you have one process and you fork that process, and what happens, it actually takes the page table, the phone book, and it will copy that phone book. It literally Xerox that phone book and place it into another process. So at that point, those two processes are literally identical to each other. That doesn't mean that physical memory gets, application gets put into memory twice, because it actually links to each other. So what we happen here is that we have an application, 1A, B, C, and we fork that, so we get a 1A, B, C after that as well, but they all point to the same physical memory block, 1A, B, and C. Now, those two processes will run independently from each other, and they will do separate things. So what can happen is that that second process actually changes something in the B block. So it changes a number, for instance. At that point, it cannot change it inside that physical block, because the physical block is also mapped to the process 1. So if you change that into process 2, it will automatically change that in process 1 as well, because they are linked together. This is pretty much the same thing what can happen with references in PHP as well. Those are linked. What happens at that point? The virtual page table can actually see that, okay, I'm going to write something to a block that has been cloned, basically. So what I need to do is copy that data block, that 1B block, into 2B block, and change the data in there. So what it does, as soon as you change something in a block, it will copy that block into a new block, change something in a block, so only the data is changed when you only is changed in process 2 and not in process 1. This is basically what's copy on write in PHP as well. Copy on write is literally this as well. So copy on write is not new thing that PHP invented, but is actually all very old, because operating systems do it a long time. So if we have an application, for instance PHP FPM forks itself a lot of times. So in this case we have like 6 forks of PHP FPM. That doesn't mean that PHP FPM is 6 times in memory. It most likely is only 1 time in memory and 6 processes linked to the same physical blocks. As soon as those applications start to run, because you do requests on them, they get to a certain process, and that process changes something. New blocks are created just by that process. And this is why it's really hard to actually figure out how much memory are we using, because we don't know how many blocks are actually copied on write. We cannot know how many code is actually being shared by other blocks. It's way too difficult for that. So this is why it's really hard to figure out how much memory are we using, because it depends on so many factors that is out of control. So we pretty much cannot know that. So as a recap, don't worry about high virtual memory usage. Virtual memory usage only means that it's a large phone book, it's a large page table. Doesn't mean that we allocated memory, but we did not use memory. If you want to see how much memory some process is using, you should take a look at the res field, or the residential memory set, because that's a more likely number to be correct. But even when you're forking memory usage, even the residential memory set will become very hard to manage and detect. And whatever you do, don't try to swap, because swapping makes your system go so slow because it needs to load all the physical blocks back from disk. If you want to know a little bit more about this, there are some really cool links to there. There's also one in there about how PHP arrays work, at least how they used to work, because they have changed a little bit. But you can take a look at that. And also some links about how Linux reports the memory and how it actually works. Okay, any questions? Yes? No.
With 32 gigabytes of RAM and even reserved free memory is shown there's all from time to time small usage of swap. Could it be that the system,
Yeah.
there's some amount of time that it believes it will never use it again,
Yeah.
and leaves it there?
That's correct. Memory is being, even if you still have a lot of memory in your system free, then your system will most likely swap old blocks that are never used out of the system as well. In Linux, you can actually configure that as well to say, okay, I really don't want you to use swap unless really needed. But in normal systems, it will swap out the things that it really doesn't need. It's most likely not a lot of swap that's being used. So as long as you have only a few megabytes, for instance, of swap, that's perfectly fine. There's no problem whatsoever. Okay, one more?
So what is a good way then to answer the question, should I be worried about my system memory right now?
Yeah, again, that's a really hard question. I hope by now that you know why. But free and top are actually applications that give you a good estimate. It always is an estimate. It's never a complete truth about your memory usage, but you can use it as an estimate. And especially when you are, you have to realize as well that as soon as you start using a lot of memory, your caching, your buffers and cache will actually degrade or get smaller, which means that your system will get a little bit less responsive because every time you want to do something on disk, it can't use the cache anymore. So you always have to make sure that you don't use all the memory of your system because it's really nice to have some memory left for buffers and cache as well. Okay.
So
Yeah.
on a Mac, you can look at the memory pressure. Is that any relation to anything we've...
The memory pressure of the Mac. To be honest, I never looked in that.
Okay.
And even though I have a Mac, but I've never looked into what it exactly is, to be honest, so I can't answer. We can look it up later on, but if you... one more?
So if I don't care about free memory on my system, but I do know that there's an application or process running there that has been forked a number of times, is there a tool to see how many pages in those processes were shared?
Can you see how many pages are shared after fork, basically?
For example,
Yeah, that's really hard to figure out because your system doesn't really register that information. So as soon as you fork a process, basically what happens is it says, okay, suppose you have 60 megabytes of memory in your application, and you're going to fork that process, then there's going to be a second process that also uses 60 megabytes of memory. At the time of forking, those two are exactly the same, so it only uses one time that 60 megabytes. But as soon as you start using those applications, blocks will change, and those 60 megabytes that was before are not linked to each other anymore.
Does it need to keep track of a sort of a reference count, or because when you change something in a shared page,
Yeah.
it needs to copy that,
Yeah.
and then modify it before it can actually store that information. So it needs to store somewhere the fact that the page is shared between more than one process.
Yeah, but that's a flag in the page table.
And it's not something you can look into.
Not that I'm aware of, because that doesn't say it's actually being copied. It only says that if you're going to use it, please copy it first. But it can be shared by one application, but it can be also shared by 10 applications at the same time. It's way more difficult than I explain it, but it's really hard to get that right. But I don't think there are real tools for that. Would be nice though. One in the back.
What is the alternative to forking in PHP ecosystem?
The alternative.
To forking in PHP ecosystem?
Why wouldn't you want to fork in PHP?
But you said it that it's not so good to fork.
No, forking is good. Swapping is bad. Yeah. No, forking is the thing is, if you fork something, it's really a simple process because it only copies the references to data. So it doesn't use a lot more data. Only when you start to use the application, it's going to use more data.
Yeah, but then we'll be in a situation that we cannot see how mail is used.
Yeah.
because of this.
That is true.
Yeah.
Yeah. So you always have to be careful when you fork something like 100 times. Is that then you cannot really see anymore what kind of memory is the application using. That's true. Okay, any more questions? Cool. Okay, thank you. If you have any more questions, then feel free to ask me after the talk.